I am John Askew. I'm on Mastodon, GitHub, different Discord servers, Twitch. I cannot claim to be a mathematician. I did a long time ago study math in college and grad school and TA'd for a little bit before falling backwards into a career in information security. Also, don't claim to be a great teacher, but I'm not really going to try to teach anything today. I'm just going to try to raise some awareness, point out some connections to math and offensive security, and maybe spark a little bit of interest in further study for some of you. Hopefully, if you're watching this, you're interested in mathematics to some extent. You might not be a math person, but maybe you're a little bit curious about it. And hopefully, you're also interested a little bit in offensive security and how there might be some connections. If you are a mathematician in this talk watching, you might enjoy pointing out all the errors in my presentation because I'm going to try to breeze through a whole bunch of stuff. I'm not going to be super precise, and there's probably there's a good chance there's some flat out errors in here somewhere, but it's okay because all models are wrong, but some are useful. And this is math. This is actually a picture taken from the Math Stack Exchange based on questions that were asked and the subjects and how those connected to one another. I think it does a pretty good job of showcasing some of the main areas of mathematics and how broad the whole thing is. Obviously, it's a huge discipline or field, and I'm not going to be able to cover even a small bit of this in 30 minutes. So I've tried to cherry pick a few things that I think are interesting and maybe can show some use or applicability to different types of offensive security things. And picking those things out was kind of difficult. I went back and forth, and the thing I finally decided to start with was probability theory. I think that's a great place to begin for a number of reasons. It's something that we kind of have an intuition about. It takes that intuition about making decisions and it attempts to quantify it. So I think we can all relate to it at least a little bit. It's useful in all sorts of places, pretty much everywhere. If you've got a decent foundation in understanding probability and statistics to a lesser extent, I think you're well equipped to be able to use that in a lot of different areas in life and in the workplace. And also, the universe might actually run on probability theory. If you've followed the developments of quantum mechanics over the past, century or whatever, and up until most recently last year's Nobel Prize, which went to a proof for the universe is not locally real, which has a lot to unpack there. You could probably find a good YouTube video or something on that, but this did not. It basically says that at a real fundamental level, the universe might be governed by probability rather than determinism. And Einstein did not like this very much. He said, purportedly, God does not play dice, to which another physicist, Niels Bohr, replied, supposedly, stop telling God what to do. And I thought that was kind of funny. But what is probability exactly? So when we're talking about probability, we're talking about a quantity P that measures our certainty or uncertainty about X. And I'm going to be speaking from a Bayesian probability perspective, which I don't know if you've heard the term Bayesian before. For me, the first time I heard it was in relation to spam filtering, like Bayesian spam filtering. And so I always, for a long time, thought it was a specific technique that was used that worked well for spam filtering. And that was true to an extent, but at a larger scale, Bayesian probability and statistics is more like a philosophy or an approach to this idea of probability, where we think of probability as more of a belief or an educated understanding of certainty or uncertainty. We can say that P of X equals 1, the probability of X equals 1 means that X is certainly true, or P of X equals 0 means that X is certainly false. And those are the two most useless and interesting probabilities you can encounter. We won't really use those much, but everything else in between is a lot more interesting. For instance, P of X equals 0.5 or 50% if you want. That means that we believe something is equally likely to either be true or false, or to occur or not to occur. And when we're able to quantify a single thing, we can then combine them with other things, assuming that they are independent things. So we can combine things with an and. That basically means multiplying the probabilities. If we believe that a fair coin flip is going to end in heads 50% of the time, then we believe that 3 coin flips of that same coin occurring all 3 times as heads would be about 12.5% because we'd multiply 0.5 times 0.5 times 0.5. So we can and logically and probabilities together. We can also negate probabilities. So not means basically subtracting that probability from 1. So taking those 3 coin flips, the probability that any one of those is tails is equal to the probability of 1 minus is equal to 1 minus the probability that all 3 landed on heads, which would end up being about 88.5%. Another way of saying this might be if there's a 50% chance, if you think there's a 50% chance that any given EDR product is going to detect your payload when you run it, and then you go and run that payload on a host that has 3 different EDRs running, then you believe that there is an 88.5% chance to be caught by at least one of those EDR products. Now, that doesn't really sound right, though. And the reason that is the case is because of this independence that I was talking about. Those events all have to be independent in order for this multiplication to work. And in fact, EDR detections are not independent. If one EDR detects your payload, then it's going to be more likely that others will as well because they share payloads. They're going to use similar heuristic techniques, things like that. And you also kind of get an intuitive understanding that that's the case, just from experience, running things on VirusTotal. It's rare that you're just going to get one. You're going to get a lot more than one, more often than not. You can also combine with or. That's basically adding, although there's a subtraction that you have to do at the end if events are not mutually exclusive. We're not really going to worry too much about that right now. But this is all for independent probabilities. It's really cool how you can combine them. When we talk about conditional probabilities, though, things get more interesting. We'll just say that. So Bayes' theorem is one of the most fundamental theorems in probability theory. And you can read the formula here. But basically, this lines up with, it lets us work with conditional probabilities. And more importantly, it really lines up with how we update our beliefs based on new information. On the right-hand side here, P of A, we have something called a prior. That's basically represents our belief about the probability at the beginning of an experiment or prior to an experiment. And then the likelihood factor kind of represents our what we determine the likelihood of our observations to be. So we do some observations, we do some science, and we determine the probability that those things would have happened. And we combine that with the prior to get what we call our posterior probability, which is our updated belief. Now that we've got new information, what do we believe now and how's it changed? And that lines up a lot with our intuition. Hopefully, when we receive new information, we're reevaluating what we believe, how likely we believe something to be. Like you might not believe in UFOs, and then you might get some misinformation or some theories from unreliable sources that say a UFO thing happened. That's not going to change your belief that much. But then if the U.S. government releases video and releases press releases and public statements about these unidentified aerial phenomena, that might have more weight on how you change what you believe about that thing. Hopefully, anyways, right? That's what we want. And this actually allows us to quantify that, which is really cool. It works for discrete probabilities, like when we're talking about coin flips and stuff. but it also works for probability distributions. And we need to talk about that a little bit before we drill into our experiment. So probability distributions tell us what we believe about a value and where it might lie. So this big one here on the left is there's different examples of what we call the normal distribution. You've probably heard of the bell curve before. It's a symmetric curve with a peak at the middle, and it may be wide or narrow, and it's parameterized by a mean or average. That's where that peak occurs on the x-axis, and it's also parameterized by a standard deviation, which tells you how wide or narrow that is. And the area underneath that curve kind of gives you the your belief or probability about where that value actually lies. And this thing occurs everywhere, right? From human height falls on this curve. A lot of other things in biology, physics. If you've seen the the Plinko game, on where that thing falls at the end is governed kind of by the same probability distribution. Economics, stock returns, you see it everywhere, and there's a reason for that we won't go into. But another important, before I get started here on the experiment, is the another distribution that's important is the uniform distribution in the top right. And for that one, we have, it represents this belief that it's equally likely that our value actually falls anywhere between A and B on that x-axis, but nowhere outside of A and B. So that allows us to express a belief that doesn't have a whole lot of bias. It could be anywhere in that range, and that's pretty useful as well. For an application of this, I thought it would be kind of neat to talk about timing attacks. So if you are familiar with software vulnerabilities, it's particularly hard to write software without some type of side channel leakage, including timing leaks, because you have to be real intentional about it, and it's real easy for that to crop up. And if those leakages are exploitable, then we end up with a timing attack where there's actual vulnerability we can exploit. So I've written a little Python Flask application here that has a timing leak. We've got a hard-coded auth token, which is 16 bytes of the capital A character, or hex 41. We've got a single URL we can query, which, if we send an authorization header with a bearer token, it will compare our bearer token to the hard-coded one. And if it's correct, we'll get a 200, an HTTP 200 response back. If it's not correct, we'll get a HTTP 403 forbidden back. And then the way it compares the two tokens is, assuming that they are both the same length, then it starts at the first byte, and it compares the first byte of our bearer token with the first byte of the hard-coded auth token. We've actually introduced a little bit of an artificial time delay here to make the difference more pronounced. But if those don't match, then this loop returns immediately. If it goes on to, then it goes on to the second byte and compares the second byte. So if you have something that's correct except for the very last byte of the bearer token, then this is going to go through a loop 16 times before it finally rejects it. So there's a difference in the amount of times it goes through the loop. There's a difference in the amount of time the computation takes. And I've also written another Python script to measure this. We've got two hard-coded values. Token A is going to be incorrect in the first byte, and token B is going to be incorrect in the second byte. And we're going to basically make two requests. Request A sends token A, and request B sends token B. We're going to measure how long each one takes, and then calculate the difference. And we're going to do that 1,000 times. Now, I've actually already run that. So we'll come over here. I've got a Jupyter notebook where we've set up an experiment. Our hypothesis is there's no significant timing difference between A and B. And if there's no timing difference, then the difference in the time should average out to around 0. In more mathematical terms, our samples should roughly correspond to a normal distribution with a mean of 0, because network latency kind of falls into a normal distribution of randomness. Not exactly, but close enough. And then we'll try to disprove this. If we can disprove this, or if we can say that the mean is definitely not 0, then that will tell us there is a significant timing difference and it might be exploitable. And let's start by just looking at the samples we got back from our measurement. If we look at that, they all fall pretty high up. The x-axis here is microseconds. So most of the samples, most of the differences were actually between 90 milliseconds and 100 milliseconds, nowhere near 0. We don't have any of this curve really close to 0. So I think it's very strong evidence that there is a timing leak. But just eyeballing it doesn't let us do any of the fun math or use the tooling. So we're going to go back and actually remove the time delay and save that. Then our server should restart. We're going to rerun the measurement. So now we've got a new set of data. We're going to go back and look at the new histogram. And that is right there on 0, right? We're actually going to zoom in because we got a few crazy outliers, but almost all of it is probably in like range negative 200 to positive 200. Yeah, if we zoom in, it looks much more like a normal distribution that's centered around 0. And it's pretty hard to tell what that mean actually is. So what we'll do for our experiment, we've collected the data, but then we're going to use something called pyMC, which is a Python library that lets us do Bayesian statistics, basically. It's called MCMC, or Markov chain Monte Carlo, but it's basically using that Bayes theorem. We're going to set a prior, which let's just say we believe that our mean mu is anywhere between negative 50 and positive 50, somewhere in here. We don't really have any strong inclination, so we're going to use the uniform distribution across those values. We'll guess a standard deviation of around 50, and we'll plug in our sample observations and generate a normal distribution from all of this. This stuff is just kind of boilerplate. The nuts algorithm is like the normal algorithm that you'd use in pyMC for this kind of thing. And we'll do about 20,000 samples and plot out our posterior distribution of the standard deviation, mu. And we're actually see that it ends up not being close to 0. We're somewhere in the range of negative 12 to negative 9 microseconds off. So there is a measurable timing difference still, or at least according to this experiment, there is evidence to support a timing difference. If we're good scientists, we'll want to be able to reproduce our results multiple times, so on and so forth. But that's good enough for a demo, right? Now you might be saying, John, that's all well and good, but that is that's on localhost, so you're not getting really any network latency there. And I would say, yes, that's true, but one, you might be surprised how accurate timing you can get across a network. And two, across a network is kind of a fuzzy concept now when you've got most stuff running in the cloud, and I can run my own stuff in the cloud on the same local network, or maybe even on the same virtual host as the thing I'm targeting. So that was using pyMC. That's a Python library for doing Bayesian statistics. If you want to learn more about that, I have to plug Will Kurt's No Starch book, Bayesian Statistics the Fun Way. It's a great intro to Bayesian probability and statistics, and one of my favorite intro math books, period, I think. There's also this open source book, Bayesian Methods for Hackers, by Cam Davidson-Pilon, who this is a great resource for learning pyMC and how to apply it. It's open source on GitHub, lots of Jupyter notebooks to showcase different types of experiments. I'd like to end on algebra just because I think that algebra is another area where there's a lot of application. We deal with manipulation of variables, but you've got lots of different, basically any other area of math you can apply algebra to. And I'd like to apply algebra to software programs. So here we've got a real simple Python program that takes an integer as input, and we've got several potential outputs. It can either say bad input or it can say success. And we can think of X as our input or our source, and say we want to make it print success. We'll call that part of the program our target or sink. We can do kind of a graph thing where we look at all the branches, all the places where it branches, if else, and look at constraints. So if we want it to hit the first else, we need X to be greater than 2, right? And if we want it to hit the second else, then we need it to be, again, less than 4. So we can actually build up some equations or inequalities that represent this path. And then we can find a solution, right? X has to be greater than 2 and less than 4. So a potential solution is X equals 3. Now we're going to take a huge leap from that to like a real program where things are potentially a lot more complex. We might have loops. We might have lots of different other types of variables, not just integers. But it still kind of applies. We can have a lot of these equations or inequalities that we can solve for to say something about our program. And that's where you have these things called SAT solvers and SMT solvers. A SAT solver looks at a very specific problem and finds ways to solve it somewhat efficiently. And then an SMT solver takes other types of problems and turns them into SAT problems. And then we can think about computer programs as with variables and dependent values. We can turn all that kind of stuff into bit vectors and plug bit vectors into SMT solvers and find solutions to much more complex programs than the one that we just showcased. This is used in software verification, access control, analysis, lots of different things. If you want to play around with this idea, look at some symbolic execution frameworks. You might have heard of symbolic execution before. And it's basically a much more complicated version of what I did at the beginning of this algebra section. Just looking at a program and finding solving constraints. I'll just stop there. Hopefully that made sense.
Thanks for watching. Achieve your next level of skills with training courses at antisyphontraining.com.